We could set up a mass spring oscillator, a horizontal mass spring oscillator pretty easily. And that's just by, if we had just a wall or something vertical, we could attach a spring to it and then attach a mass to the end of the spring. So if this is at equilibrium where the spring is completely unstretched, what we can do is we can pull back on the spring. So if we stretch out the spring, to kind of show this exaggerated just a little bit. If we pull back on the spring and if we were to let it go, what's going to happen is this mass is going to shoot back to the equilibrium spot. And the mass is going to shoot back to the equilibrium spot if we were to completely get rid of friction. So if there's no damping involved here, what would happen is we would overshoot our equilibrium position and we'd have a compressed spring with the mass. Now, ideally, these distances should be the same. So it's not drawn perfectly, but we would have this maximum amplitude that it would be displaced from the equilibrium position on the other side. So the two distances would be identical. They would be equal to each other. So what I'm going to do here is I'm just going to place a few different dots. So I'll have a dot here at equilibrium. I'll have a dot here at the maximum amplitude. I'll have a dot here at the maximum amplitude on the other side, and then a couple of dots in between those two different spots. So what we're going to do is we're going to take a look at what's happening with the forces at each of these different spots. Equilibrium is a pretty straightforward one when we're talking about a horizontal oscillator because we have a force of gravity, we're going to have a normal force, but we're not going to have any force in the horizontal direction because the spring is completely unstretched. So we have a net force, a horizontal net force of 0 newtons at that spot, which is helpful. At the very end, what's going to happen is we're going to have a force that's inward. So we have a force that's inward, and that's the force that's caused by the spring. So the force on the spring is equal to negative k times x, where x is going to be our displacement. So it's important to understand that it's negative because it is inward. It's opposite the direction of motion. So we know that the spring was moving to the right. We have this force that's going against it to the left. So we have this negative spring force. It's dependent on the spring constant, but it's also dependent on the displacement. So what happens is if we look at this spot in between, we still have our spring force. It's still negative kx, but it's not going to be as great of a force because it doesn't have as much of a displacement here. The spring is not stretched out as far, so the magnitude of the spring force is going to be less. On the other side, the same thing occurs. We have kind of a small spring force, negative kx, and then we have a greater spring force at the very last equilibrium, negative kx, but is greater than it was before. So the force is constantly changing as this mass is oscillating back and forth. What you need to know is that the direction of the spring force is always towards the center. So the direction of the spring force is always towards the equilibrium position. Because of that, this spring force is a restoring force. So the restoring force is the force that's sending this mass back towards the equilibrium position where it has no net force. So the spring force is changing. So basically, if we start from the left, it's decreasing, 0, then increasing and increasing again in the opposite direction. Then going back, decreasing, 0, increasing, decreasing, 0, increasing. So this force is oscillating. So this force is oscillating back and forth. Since the force is oscillating, the acceleration is oscillating as well. In fact, the acceleration is in the same direction with a proportional magnitude to that spring force. So the acceleration is the greatest at the endpoints, the greatest displacements, and then it starts to shrink. It's smaller and smaller and smaller. There's no acceleration in the very middle, and then it's getting bigger and bigger and bigger again in the opposite direction. So the acceleration has a proportional relationship to that spring force. One more distinction I want to make is that if we call these these maximum displacements A. So I'm going to call this positive A for a positive amplitude, negative A for a negative amplitude. We can also simplify our spring force at the very end, because we can say that the spring force is equal to negative K times A. And on the other side, the spring force is equal to negative K times negative A. So it's just going to be a positive K times A just because of the direction that we have there. So the spring force at our greatest amplitude, if we knew what the greatest amplitude were, we can find the spring force at that greatest amplitude just by plugging in A for our x value, and that's how we're going to get our force.